Hello everyone, it's December 29th. Well, quite an eventful day today. Brought my cats to the vet and then did almost all the data analysis plot for the paper. Still have 2 more left, but I think I can get them done pretty soon. So tomorrow I can put together a better presentation, a better outline of how the paper is going to be. All right, so, I cheated. I took a look, not on the hint here, but I was just trying to figure out how do we do unique permutation. There's actually the question here called permutation 2. And I did it many times, but I forgot how to do it. So I actually went back to look at that. How do you do permutation? And now I know how you do permutation, which we can definitely leverage here as well. So yeah, we can try. But still, even if I know how to do permutation, it's basically a backtracking strategy. But even if we do, and on the other hand, we know that this is going to be pattern based, right? So like this and this, like if we have ABB and CDD, we don't have to redo it. So we know all that, but man, I still feel like there's got to be more levels of memorization in this thing. Yeah, that's just my opinion. I think there's more, but I don't know. I mean, like, how? Yeah, exactly. Like, what do you mean, right? What do you mean? Like, how many more are we having there? Yeah, because the algorithm to find the number of permutations is very, very bad. Take a long time. I mean, we can actually try. Yeah. P. Let's see. How long does it take for this? I think if we use that. That was so fast. I don't know. Maybe it's not that bad. Maybe it's not. And I'm not quite sure how am I supposed to approach this pattern, right? We need pattern. Yeah, I don't know. I feel like even if you use that algorithm, this one's gonna time out. Yeah, we can actually go take a look right now with permutation. This one. Right, I've done it many times. I was able to do it in the past, but then I forgot how to do it. Yeah, I forgot how to do it. Yeah, permutation. What's the runtime for this? No, I still think there got to be an easier way. You can't just say use this, but we can even put this one in there and then we can try. But I mean, we don't have to keep things. We can just add on top. But I think that's still not gonna be right. don't know, man. I don't know. Yes, it's like at least you have to do that many times. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, I don't think that's the way to go. I mean, that's the way to find permutations if you need to list them, right? You need to list them out. So this definitely is something else. That's not right. Well, I mean, good thing is we kind of get a refresh of how to do permutation. Right? You gotta refresh how to do. Do you know how to do permutation? The other one? Oh, the other one is actually simple. We just put it at all positions. So the other one is not that hard. I mean, honestly, this one's not that hard either. You just every time you just append. You put this and then you do permutation for the remaining. Right? Man, I kind of forgot again. Or did you append to the end? You append to the end every time you append, and then you backtrack the current. Every time you just append and you backtrack, append, backtrack, and then you will go through every single one, right? If you go through every single one, and you'll pop, you try another one. I mean, I think this works for this works for the regular as well. Just for the regular, you don't have to use a counter, right? You just keep track on the, I think the regular you would just keep track on the index, right? Because every time you just move down to the next index, because you can only go down. Is that right? That's every time you go through the entire counter. Every time you go through the entire thing. And I remember the permutation is slightly different. You know what? That piques my interest. I forgot how to do all these things. This permutation is the original permutation. Insert. It's the insert of this one. We got a remainder, and then we just insert at every single spot. That's how we do this. Yep. So that's the regular 2019. Oh. What the hell? And no. Don't dwell on this. We need a good solution. Yeah, this one's the insert. I don't think that's the. What's this? All the permutation, yeah. Oh, psh. This is cheating. I don't know what this one is. Oh, this is. No, what I remember is to insert in the middle. I don't know why I have to do factorial here. Why do I do a factorial here? What the hell is k? K is index. And I compute a factorial of index. A factorial of index. and I have a base. And wait, what? I have no idea what I was doing here. No idea. I have my understanding of permutation. It's not doing this way. So regular permute, you can permute the remaining, and then you insert the first letter into all possible positions, because that's what permutation is. And every time you just repeat, and then you're done. But if it's a permutation of non-repeating, then you use the ideal of, you can use the ideal of the non-repeating on the regular permutation as well. But my point is, this is definitely not, because you just cannot do it this way. You cannot do it this way. Yep. Yeah, let's get today's done and then go back to that. All paths from source to target. A directed acyclic graph. End nodes, okay, for all possible paths from 0 to n-1, and return them in any order. So 0, 1, 3, 0, 2, 3, 0, 1, 4. So it's just a DFS. No. It will be BFS. Which one is easier to write? DFS every time we hit, right? And then we keep tracking. Maybe DFS is easier to write. Hey, year is about to end, man. Do you think you have achieved anything this year? I read a lot, much more than before. So that's something. And then, the more you read, the more you become less afraid when a book is huge. I'm reading a book now, it's like 350 pages. I was like, okay. This one has a lot of words at 350 pages, so it'll take a while. But, you'll be like, nah, it's alright. It's not too big a deal. Directed, acyclic, so we won't go back. So we don't even have to check. We just keep moving. Huh. We don't have to check if they visited or not. Because it's acyclic, because it's directed, right? So we won't go back the same edge. It's acyclic, so there will be no cycle. So I can just go, I can call it index, and what is current path, right? And we don't report anything. And now we have a result is going to be this. So it does not have to return any order, right? In any order. Okay, so basically if index is equal to, didn't give me n, okay, I have to do n myself. Rest.append path. Do we have to backtrack? Else what? Else we're gonna say current.append index for next in graph index. Why it didn't There is something wrong. I don't know why. For next in this graph, what do? The DFS next current. Right? And then once we're done, pop. DFS on 0. I'll return on the rest. Yeah, let's give this a shot. And I'm not interested in doing the my bad. I forgot. Not interested in doing the other one. What? Current. Why do you say current? Huh? Why would I say current? Because earlier I had a solution that used current. There's more. Oh God. That's really embarrassing. I put current in all of them. And it's not correct. What? Bonkers. I know. It's bonkers. Huh. I think I know. I forgot to add the last one. Alright, this one should be right. I forgot to add the last one. There we go. Yeah, I don't want to do BFS. It's the same thing. All right, I hear what you're saying. Basically, just don't be lazy, you know? And if you have a chance to practice, it's definitely always good. If you keep not practicing, then eventually you will lose the ability. I hear you. How we didn't do this? Q shall be the path, right? Oh. Okay, for path in Q, all right? And then temp. So each path come out, and we can check if path. If path last one is equal to n minus 1, then 10 path done. Else for next in graph path minus 1 temp dot append path plus next, right? Blah blah blah. When we're done, we'll return the rest. Okay, let's try this one. Is that right? Oh no, I forgot. Q equals temp. Yeah, we put it to timeout. Yep, looks about right. Okay, so that's that. Yeah. What else do you have? If I tell you I don't have anything, do you even believe me? Yeah, it's guaranteed. We cannot list everything out. We have to find a way to compute. I mean, what if we... Yeah, it's the same question. Like, if I know the full permutation of 1, right? If I have a pattern and I know its full permutation, can I know the permutation when I add another one? How do I even get there? And if we have 2, well, we were trying that the other day, like AABB, right? We can fix B, and we can say we try to add A on top of it. But hint. Yes, that's just... Yes, I can do that. Because that is just... You know what? Give me a thought. I know AAB is 3. ABC is 6. Right? Because that's 3 factorial. And we can actually check to see the similarity between the two. Okay? So if AAB okay, that's the 6, and then we have the same thing like this one, and this one's the same. This one and this one's the same, and these two are the same. So when two things are the same, it's because of what? It's because at that position we have a swap. Yeah, we do have a swap. So are you telling me that each pair of this can have this swap effect? What are you saying? You're saying, what if we do a ABCD and we do a AABB? Well, ABC will have 16, right? And then try ABCD is 16 based on what we do. That's 16. Just double check. No, it's not 16. Come on, 1 times 2 times 3 times 4. That's 4. That's 24. I don't know what you count with 16. How many is this? So from my idea, right? We have AA, we have 2 A's, and we have 2 B's. So for 2A, we're gonna have, because in total we have 24. So amount of 24, 12 of them will be, because amount of 24 we have these 2 A's, and because their position can swap, right? So in one position we have 12, and the other position, so we get rid of them. So we only have 12. Then we have BB. So among this 12, we have BB. So 6. We say this equals 6. Is that 6? It is 6. What about AAAB? Huh? How about AA again? We have 24, right? But we have 3A. Any pair can cause issue. So we can say 3 choose 2. So we have 3 types of pairing. So the first type of pairing, we divided 24 by 2. Second type of pairing, we divide. Third type of pairing, we divide. So that will be 3. Did I just say 3? You did. Shoot. It's now 3, man. Yeah, like if it was these two paired together, so we have 24 of them, right? Basically, it will be 12 of them, and then they just swap. And then we get rid of them, so they will all, there'll be no swap, right? Then I pick the other 2 pair. Okay, but the other 2 pair, so 2 pair is down. So the remaining, huh? Maybe I should write it out. Right, these we can eliminate. Hold on. One, two, three, four, five, 6. Right, now we have A2 at the front and A3 at the front. Then they will all be the same, right? Okay. Then when you look at this, we have 6. But the unique ones are this Oh, we also have B at the front. Well, we can say with A at the front, we have AAB. No, I don't like this way of thinking. It should be, if it's A at the front, AAB, in total we have 6, right? 2 times 3 is 6. But they will have pairs. So we only have 3 here. And now with B at the front, we only have 1. That still feels like a... No, I don't like it. Let's go back to AABB. You say if A at the front, right? Then we should have 6. But we have a pair, so we don't have 3. Now we have B at the front, that will be 3. That's 3 plus 3. So what's the rule? Something at the front, right? We're going to find the remaining. And what if we have AAAABB, 4A2B? We can say we can have A at front. Doesn't matter which A is at front. So now we have AAABB. Right, we have this situation. And then we can say, okay, define this. We can put A at front. Now we have AABB. Now we know AABB, but we find out already that's a 4. Alright. So we can do A at front, we have 4. And B at front is going to be AAAB. And AAAB we find out. No, AABB is 6. And AAAB is 4. So that's 10. So A at front is 10. And B at front, we have AAAAB. We can do the same. Let's say B at front, A at front, we have AAAB, which is 4. B at front, which is AAA, which is 1. So that's 5. So that'll be 15. Right? Yeah, I mean, this is right, but it requires memorization of a lot of things. Like, literally a lot. It's like, it's a pattern, right? It's a pattern. I mean, the good thing is they're only at most 27 letters. 26, right? 26 letters. But it's still going to be a huge amount. Each one can be at the front, right? Then you find out how many is in the remaining. And the next one in front, how many is the remaining? And the next one in front, how many is in the remaining? And each one, we pick one in the front. Man, that's gonna take a long time to find. Keep reading. I don't think that's the right way. How? I don't know, I'm asking you. The product of the counts of distinct permutations of all words will give the final. Yeah, the this hint is just, oh god. The most important thing was not mentioned here. Like, duh, that's the final answer. Duh, how to reduce overcounting when letters are repeated. This is exactly what I do not know. And I try to find some inspiration somewhere else. I'm trying to venture, like, to create something complicated. How about this? All right, we have a pattern is 432. That's the pattern. Given this pattern, how many unique permutations do we have? Well, we have 432. Okay, what do we have? We have 1 is 1. Right, any time if it's only one thing, that's always 1. And if we have 2, 1, that's a 3. 3, 1, that's a 4, right? As long as it's 2 and the last one is a 1, we have. That's easy to do. And then we also have, yeah, it's going to be a huge hash map. Okay, 432. So what do? We say we need to compute at 432 level. It's basically 332 plus 422 plus 431, right? So that's the first one. We can split into 3. Now 332 is equal to 232, right? Oh, 332. 232 again, and 331. Okay, so this is going to be 132. 132. Oh, if we keep it sorted, 322, 322, 331. So that will be 321, 321. Have we solved 321 already? And so 321, 321, and 222. Okay, so 321 can become 221. 221, 311, and 32. All right. Try it. I mean, we have a lot of things already. So basically at each position, we're going to have however many multiplied by, yeah, and honestly, I have no idea. But let's get this one, at least try. At least try. I mean, we have this idea, I mean, whether it's valid or not, we don't know. We're gonna cheat. Okay. We need to do count unique perm. Give me a string, right? How do we count? Well, we will first form a counter. Now with the counter, we can say C equals counter S, and then say signature, or the signature key equal to tuple sorted C dot values. Okay, so that's that. And then we say, oh, we're gonna do another one. Def helper. Ha! Okay. Alright. And then this will return an integer. Don't do it this way. Key can be a tuple of integers. Right? If k is in self.memo, return self.memo. If not, because it's sorted, everyone would pick one, right? So what we're gonna do is k list equals want to turn into a list. Do you want to do that? Yeah. Then for I in range len k, okay, then we say what do we say? K list I minus equal 1 and the rest plus equal 2 self dot count tuple k list, then k list I plus equal 1. I also need to remove the zeros. Next, k equals sorted k list, and then while next k reverse equals to, oh, that we don't care. Oh, we need to pop, so reverse equals true. And while k minus 1, while not, next k dot pop, right? Eventually we can say if len k is equal to 1, we'll return 1. Right? What if it's in that situation? Now we have 1 plus okay. So we pop all the zeros. And then okay, well you go to res. And then return res. Okay, and for equal, no, C equals counter word. And sum k equal to len k. So everyone is 1. So math dot factorial. Right, we're going to say C equals this. Res multiply equal to self dot count unique. Tuple sorted. Sorry, what? Sorted C dot values. Reverse equals true. Okay. Huh. That's interesting. Well, we have, let's put these in. Remember, ABV is 6. That's 15. That's what I remember. Okay, we have issue immediately. Oh, this one's right. Huh? Oh, self.memo. Okay. Self.memo. Okay. Okay, it's not 100% correct. ABB is not right. No, it's 10. I was right. I delete my previous. I don't even have to go all the way down. Just try this one. Wait, do we have... No, we don't have that, so can't. Try it, see how it goes. Nah. Nah, I don't think that's the solution. Even though I have memoed every single thing, there are too many possibilities out there. No, that's not right. Hey, it is an attempt, right? It is an attempt. Yeah, gotta be other ways. All right, well, we'll save this for tomorrow. I don't want to check the answer now. I think I still have a little bit more in me. Yeah, I'll try this tomorrow. I'll see you guys tomorrow.